Good afternoon. So let's immediately pick up where we left off from the last class. So as you remember, we were trying to consider or try to understand how to approach the white noise forcing limit of a Langevin equation, right, which to start with is being forced with some correlated noise so that it remains a standard ODE. So finally, we formulated our problem in the following precise way. Right? So we said we have an equation for x, right, which is our dynamical variable evolving on relatively slow time scales. And that has a deterministic part of its evolution, which is in this function small a, which is in general a function of x and t. Right? So this is the drift part. And then we have added in Langevin style a kind of forcing, right, with coefficient b, which again can be a function of x and t. Right? And then the forcing has been put here in this alpha by epsilon, where alpha was some stochastic Markov process, continuous stochastic Markov process, but correlated. Okay, this 1 by epsilon is important because epsilon square holds the ratio of time scales. And we'll see that in a second. So we now need an equation for alpha, and because we said it's a continuous Markov process, we can always write some Fokker-Planck for it, for which we can again write an SDE. Right? So this is the SDE for alpha. Right? So alpha then evolves again with some potent drift, and ultimately being driven by some Wiener process. Okay, so this is white in time, right, which drives alpha, but because it has these other terms, alpha itself is correlated. So this is like a standard Ornstein-Uhlenbeck process. So even though this is white in time, you can see that the solution of alpha will be the stochastic integral of this. Right? So because you're integrating over the white noise, the result will of course be correlated in time. Right? So alpha itself is correlated, and the alpha is being used in x. So we could just solve x like a normal ODE once we integrate out alpha. Okay? So there's no problem with this as long as epsilon is finite. And epsilon square, as I said, holds the ratio of time scales. That's why it comes like dt by epsilon square, but dw by epsilon, because remember, increments of the Wiener process go like root t. Okay? Fine. So now the point is that when epsilon goes to 0, we'll get this singular limit of white noise, right, where you will have alpha itself starting to fluctuate like a white noise process, okay, because if you like, the time correlation is sitting here, right, and that is shrinking to 0 as epsilon goes to 0. Right? And to account for that, so that it doesn't vanish here, you have a 1 by epsilon, so that it gives you the white noise behavior of infinite variance, but delta correlation in time. So all this we saw in the last class. Now we have formulated in this precise way, and all we need is to take the limit of epsilon going to 0 and see what happens. But now doing such a singular perturbation calculation with these SDs is something alien, but we can bring it into a familiar problem by looking at the corresponding Fokker-Planck equation in x and alpha space. Okay, so that's what we did here, and the moment we do this, we see we now have a PD, right, with some time scale separation in different directions. So alpha is like a fast direction, x is a slow direction, and in that sense, it's analogous to the Taylor-Harris problem. Okay. Also that we discussed in the last class. So here is the final statement where these are three operators which we can write in this way. This L1 is the dominant operator as epsilon goes to 0. Okay, so remember we had said this is the scaling, this is the form you get if you scale with a slow time. If you scale with a fast time, then you would pull in the epsilon square here, and you would instead get L1 plus epsilon L2 plus epsilon square L3. So we'll proceed with this. Okay. Now what we want to do immediately is, once we recognize the singular nature of the problem, either by, in the fast time scale, realizing that as epsilon goes to 0, you will get dp dt is equal to L1p, and L1 has a null space. Or if I just multiply throughout by epsilon square, set it to 0, I'll find L1p equal to 0, which has a non-trivial solution only if L1 has a null space. Either way, we'll recognize that I need to now find the null space of L1, and that will form the coordinate for a center manifold reduction, or a Lyapunov-Schmidt reduction. Okay. So then we came to the question, does L1 have a null space? Okay. And what we want to do now is to reach some conclusions that are independent of what exactly this A and B is, or in other words, what exactly L1 is. So we will use properties. The only general property we know is that L1 itself is an operator in a Fokker-Planck equation, right? Because the evolution of alpha is independent of x. I can write this combined Fokker-Planck for both of them, but I can also see a separate Fokker-Planck equation, right, of just, suppose I consider the property distribution of just the alpha process. Right? the evolution of this PDF, which is just the alpha process, because that's anyway an independent equation. Right, so that Foucault-Planck will be just this. So what I will use again and again is the fact that I don't want to specify precisely what L1 is, because I want to get a result for some general capital A, capital B. So what I know now, the only thing I'm going to use is that L1 is an operator of this genuine Foucault-Planck equation. Okay, so what that means is that if I choose some initial condition, right, initial distribution for P prime, so P prime of 0, whatever it may be, right, as long as it's a normalized PDF, even otherwise actually you take any initial condition for this P prime at 0, and if you solve this equation, what will you get at the end as t goes to infinity? You will get the stationary distribution. Right? So if I were to solve this equation formally, right, I can write P prime is equal to okay, so I'm treating, remember L1 is a operator. You can define the exponential of an operator the same way define exponential of a matrix, right? So this exponent of L1t is itself an operator which can act on this function, and it will give you the P prime at any time. And now I know that as t goes to infinity, right, for any P prime of 0, that means any initial distribution, it will evolve and reach the final stationary distribution, which will exist because the assumption I'm making on alpha is that it will reach stationarity, and it is in the stationary regime that I want to use alpha to force this. That is the logic. Right? So the only thing I know about alpha is it's a stochastic Markov process which is in the stationary regime. Right? That means the statistics are no longer changing. Only then I can look at its autocorrelation, right, as only a function of the time interval. That's what we started with the last class. So alpha is some stationary process. Therefore, its corresponding Foucault-Planck, we will be interested once this P prime has reached the stationary distribution. So as far as the kernel is concerned, it means there is some function, right, which is the stationary distribution of this Foucault-Planck equation, such that L1 P prime is 0, right, because as takes t tend to infinity, I will find, so PS, right, is basically the limit of t going to infinity of this guy acting on it. So I can find this PS by taking any initial condition and taking it to infinity. So I know that this stationary distribution exists. I can also find it directly by saying that the derivative of P prime must be 0 now, because that's what it means that you are at steady state, right, which means L1 PS is 0, right? That is what will happen when I reach stationarity. So clearly this thing is spanned by PS. So PS is the span is the null space of this L1 operator. Okay, and another nice takeaway from this, what I just did, is you can see that PS itself is given by acting this exponential of L1, taking it time to infinity. So this thing can be treated as an operator. Right? It's just, this is an operator, I take t going to infinity here. Right? So this operator, if it acts on any function, it will give me PS. Right? Provided that function, the only requirement on this initial condition, since it's supposed to be a PDF, is that its integral must be 1. Okay? But so what? If I take some other function, which integral is not 1, I can always normalize it, right, by some factor. So it means if I apply this on any function, I will get PS times some factor. Okay? So that's nice, we'll use it later. Right? So what it tells me is if I have this guy, and I act on some function f, because in the alpha space, right? So I'm acting on some function f, I will get PS times this, where that just means I'm taking the integral over alpha. Okay. I've not put the limits on alpha, right, because you could take it to infinity and put make it go to 0, or you can take a finite domain and put no flux boundary conditions or periodic boundary conditions, right? So any such suitable homogeneous conditions will knock off, will be fine for what we want to do. So we'll use this result later. Okay, but independently of that, we also know that PS is defined by as the null space, that L1 PS equal to 0, because obviously then for that case, automatically it's steady state of the Fokker-Planck. It's a stationary solution. Okay, so we know that the kernel is non-empty, it's spanned by PS. Moreover, PS can be obtained by action of this exponential operator. Okay. Fine, so we have the first ingredient that we need to do our center manifold reduction, right? We all want to break the domain space, right? That means we want to rewrite P, right, as some part lying in the null space plus the complement, right? In this part in the null space is what is the coordinate for the center manifold, and the remaining part we will have to approximate somehow. Right? Those are the fast degrees of freedom. Okay. And then to get those equations for the evolution of the part along the center manifold and the fast things, we'll have to project out the original equation, remember, into the range complement and the range, right? Because only then will we be able to solve this singular equation in the limit epsilon going to 0. So for this, we now need to find the range complement of L1. We found the kernel. Right? So the range complement of L1, of course, we know, right? Certainly for the Fokker-Planck type operators, is the same as the kernel of the adjoint of L1. Okay. So we had used this fact in our Taylor-Harris, but there the operator was the physical diffusion operator, and that was self-adjoint. The diffusion coefficient was constant, so it was trivial. Okay. And we saw how it was self-adjoint. In this case now, our diffusion effect is first of all this Fokker-Planck type operator, it's not physical diffusion. And this B in general can be a function of alpha. Okay. So if it was constant, it would pop out, it would be like normal diffusion. But B is in general going to be a function of alpha, right? So if you like, when you acted on P, it's half d square d alpha square B square P. So it's sitting inside the derivative. Okay. So let us now see whether it is self-adjoint or not, right? Or we'll try to find what the adjoint is. So how does one do that? You start with L1 acting on some U and take the dot product with V, and you want to find L1 star such that this is true, right? And then you have to choose the boundary conditions appropriately, so you cancel out any boundary terms. So we start with the left-hand side. So you have minus dou by dou alpha A U Okay. So we operate on U, but we multiply by V and take the integral. Okay, that's the inner product. And now what we want to do is switch the operator onto V. Okay, so you do integration by parts. Here you do it once, right? Here you do it twice, and then you will get some boundary terms. Now if you put no flux boundaries on U and V, that means the derivatives are 0. Right? Or you put periodic boundary conditions on U and V. In those cases, or you put 0 at plus minus infinity, right? In all those cases, it will cancel out. So such homogeneous boundary conditions, the boundary terms will vanish. And the derivation, in fact, you have done this multiple times, right? You also did this when we derived the Fokker-Planck equation in the beginning. So I'll not spend time here, right? We do simple integration by parts, and you should be able to show that L1 star will turn out to be plus, instead of minus on the convective operator, you get plus, right? And A will pop out. And the other term will have plus only because there are two derivatives. But now the B square will sit outside. Okay, so for example, here you can see that what I have to do is take V as the first and this term as a second, right? So first into integral of second minus integral of differential of the first integral of second. So AU will come out. So the A will stay outside the derivative. Same thing will happen when you do it twice. So the B square comes out, right? And there's a sign flip only on the convective term. Now, have you seen this operator before? Relative to the usual Fokker-Planck operator where A and B are inside the derivative. Have you seen this before where A and B come out in the early part of our course? Right, so this is exactly the backward Fokker-Planck equation operator, right? Right, it corresponds to the backward Fokker-Planck equation. If you remember, when we did the derivation, right, by taking expectation of some function, we found this operator. But when we wanted to find the evolution backward in time, we could apply the derivative definition directly and we got this. Right? It's because the way the integration by parts ultimately worked out were different. So in fact, right then I could have started with this equation, which was called the forward Fokker-Planck, and use general operator theory to show that if you have such an evolution equation for the forward, you can find the equation to go backward with the same initial condition to be the one involving the adjoint of the operator. This is a general result of operator theory. So you could have done it that way. We of course did a physical argument based derivation, but now you can see this thing also here. Okay. Anyway, so when we consider the adjoint of L1, it turns out to just to be the backward operator, which I derived. And now you can see the kernel, because it's not the same as L1, the kernel will also not be PS, right? So what is the kernel of L1 star? Right, which is the range complement of L1 onto which I need to project the equation. Right? What is it? So what function of alpha will give me L1 star equal to 0? Anyone? This is now more like the Taylor-Harris problem, right? A constant, right? So any constant will be in the kernel, so it's spanned by just 1. So of course, if I put any constant here now, it's 0 and it's 0, right? Any arbitrary constant. Okay, so you have now this situation. So we have the basis for doing our reduction, right? But it's different from Taylor-Harris precisely because the operator now is not self-adjoint. So the kernel onto which I need to project P itself or split P is PS, the stationary distribution of L1 of the Fokker-Planck for alpha. And then when I look at the codomain where I need to project the equation to get the reduced equation, I have to project it onto just 1 because that is spans the null space of the adjoint L1 star. Okay, so now let's proceed with the reduction. Okay, just as we did in the Taylor-Harris problem. So first we're going to write split P, okay? So we'll write P as the part that is projected onto the stationary distribution. Okay? So this is of course just a scalar, right? So it has to be multiplied by the function itself plus the deviation, right? We call it P tilde. Okay, and then this I can write just to make it easier for me. So this stuff, remember that These brackets means I integrated with respect to d alpha. Right? So after I do this, of course, alpha will go out. So p depends on alpha, x, and t. So what I get left over is some function only of x and t, of course. Okay, so times ps, and ps is a function of alpha. Okay, so you can see the standard splitting, which is true of the center manifold, of being on the center manifold. Right? And this p tilde has everything. But once again, I'm going to say it depends on the fast direction only through its dependence on phi. That is the assumption underlying center manifold. Sorry. Okay, so what I want to do is calculate the deviations in the alpha direction that are sitting in p tilde, but how those deviations evolve in the slow space and time direction is through being slave to phi. So phi is the coordinate along the center manifold. Okay, now the way I'm going to choose PS has already been normalized because I've called it the stationary distribution, right? So remember that I have this equal to 1, not fine. So the way I've chosen to define the projection, right, is consistent with PS being the stationary distribution. Right? So if it's a distribution, its integral must be 1. So this is not, so that means the phi is not the component of P along PS, right? If it was a component of P strictly, I should have, so if I wanted to write this as a component of PS, I should do P projected on PS divided by PS projected on PS, right, to normalize it, and then I will have PS. That's how you would do a standard thing, unless PS integrated with PS is 1. Right? So if I had normalized it this way, that the integral of PS square equal to 1, then I can say that phi is actually the component of P along PS. Right? But I'm not doing that. I've just normalized PS such that its integral alone is 1. So phi is not the component, but it still has a, in fact, for us, much more useful physical interpretation, that phi is the PDF after you average out with respect to alpha. So that's called the marginal distribution. Right? So imagine I have some distribution of, let's say there is a swimmer, right, and it is moving in space and with different orientations, and I want to just find its spatial concentration. Right? I would average out across all orientations, and that would give me, so I'll integrate out all orientations. Right? But I have to do that integral with respect to the distribution in the orientation space. Then only I will get the concentration. So at any position of time, if you want to know how many swimmers are there, right, then I would have to take swimmers of all orientations and add them up, but weighted by the distribution in orientation space. So that's exactly what this is, right? You take the full 2D PDF, you multiply it with the distribution in the alpha space, integrate out alpha. Right? So that gives you the marginal PDF. So phi is, if you like, the PDF after I integrate out alpha. Of course, in the correct weighted way. Okay, so that's in fact what we really want, because in the end I want to find an equation for phi. And if the equation for phi turns out itself to be a Fokker-Planck equation for the evolution of phi in x and t, so phi only evolves in x and t, it itself is a PDF, right, the marginal PDF. So that's what I want phi to be. I don't want it to be some component in some function space. Okay. So if I can find the Fokker-Planck equation for phi, which is the PDF in x and t only, and then I can interpret the diffusion terms as a noise, and we'll see what form the noise takes. Right now there is no noise in x, right? If you look at the full PDF for small p, there is diffusion only in alpha. X has only drift. Right? But if I get an equation for phi now, which is integral PPS, right, the marginal PDF in x and t, So if the equation for phi that I derive after my reduction has a diffusion in x, then when I go to SDE space, that diffusion term will become a noise. Right? This is what I want. Okay, so that's good. So of course, this also means that the integral of p tilde with ps is 0, right? That's because it's not in the null space. Fine. Let's now go to projecting the equation. So first, let us get the reduced equation by going on to the range complement of L1, which basically means now I multiply the equation by 1 and integrate, right? And in that equation, I shall make this substitution so that I can get my equation for phi. So now, right, so let's do this. So I have first dp dt, but p I write this way. So I'll get okay, so I take dp dt, I make the substitution, then I multiply by 1 and take the average with alpha. Okay, so when I do that, of course, I will get the average only on ps. This doesn't depend on alpha. Here the average will sit. Now I go to the other side. Let me write it in operator form, right? So I have L1 by epsilon square, right, acting on ps. The phi will come out. Phi doesn't depend on alpha, right? Okay, so L1 is acting on the ps, then L1 acts on p prime. Right? So of course I have so remember now L2 acts in x, right? So it will act on phi. The ps will come out. So in fact, I can write it this way immediately, right? Because L2 I can't do that, right? L2 has alpha sitting inside. So remember, L2 is d by dx of small b into alpha. So alpha is there, so I cannot take it out yet, right? But what I can do is, yes, let me leave it there for the moment. That I can write. Okay, any questions about this? So now we'll simplify the terms one by one. Again, trying to use what we know in general about these operators, right, without specifying capital A or capital B. Okay, so let's start. So we come to the first term, and we know that based on my normalization, the integral of ps is 1, right, as I just said. Right, so this is just going to be 1. This I can't do anything with, let it be there. Now when I come here, what will this be? Remember what ps is, right? So when L1 acts on ps, what will I get? 0, right? Because it's the null space. So the whole point of projecting is to get rid of the alpha direction, right? So that has to disappear somehow. Otherwise, what we did doesn't make sense. So this guy went off. Now this is the other operator in alpha, right? Everything else is operating in x. So it's basically become a equation in x and time, right? apart for this fellow. Okay. So let's look at this guy now. So if I say L1 P tilde, right? So let's okay, so some simplifications. Right, this is the same as taking the inner product with 1. In fact, that's exactly what we did. And then I can use the adjoint, right? And move it. And what is this? 0, right? Because 1 is in the space of that. So this guy is also gone off. Okay, so I use the adjoint property and the fact that 1 is the null space of L1 adjoint. Okay, then let's look at the term after that. So I have L2 acting on PS. Right? So this is so I can take the integral in to remove the x part, right? So minus d by dx b acting on the integral of alpha ps. Okay, so it's d by dx of b. This is also some, I mean, this is not a function of x, this is just alpha ps. So what is this now? This is, remember, taking the integral of alpha with respect to the stationary distribution. Right? So this is simply the mean of alpha in the stationary state, which is what by assumption? Right? Alpha is the noise that we are perturbing with, and we are going to use a zero mean noise. That was the assumption. Right? So this is 0. Right? So that's just because we said I'm going to choose some stochastic process alpha to drive the system, which has zero mean. So that fact will drop off this term. So again, we have not said anything specific about exactly how we are producing alpha, other than the fact that it has zero mean. So now 3 terms have dropped out. Okay. And then that term L3 phi, again we can bring PS inside. So I can't do anything with this, it will be L3 P tilde. But the operator L3 itself can be removed, right? Because L3 is just d by dx of A of x. Okay, so I can't remove these terms, but I can simplify it in the sense that L3 is acting on x, phi is a function of x, so I can take the average union on PS, that will be 1. So this term will just be L3 phi. Okay. And this term will be L3 acting on the average of P tilde. But the average of P tilde is not 0. Right? It is the projection average of P tilde multiplied by PS, which is 0. So that will survive. Okay. So finally, if you like, I can write it. Okay, so after doing all this, I have a simplified equation. So this is my equation for phi now, right, up to this point, which has, of course, some unclosed terms, which I have to deal with. Okay. So I have dou phi dou t, right, is equal to L2 P tilde, where I cannot take L2 out because alpha is sitting inside, but I'll simplify it later. Okay. So L2 P tilde by epsilon, right, plus L3 phi plus L3 the average of P tilde. And then minus this guy, of course. Okay, so far now this is my reduced equation. It ultimately, hopefully, will become a Fokker-Planck equation for the evolution of the PDF in x and t marginalized. Okay. Right now, we can see, so we can't see that form yet, of course, but what we should bear in mind to see that this will be simplifiable is that p tilde is an order smaller, right, than phi, because as epsilon goes to 0, phi is the leading component. Right? Phi is a component along the null space, which was the solution to L1 p equal to 0, which was all that survived when epsilon went to 0. Right? So now corrections to phi will all be at least order epsilon. So you see there is a 1 by epsilon here, so this is the dominant term. Right? However, this p tilde is probably also order epsilon at leading order. So the epsilons will cancel here, this will be an order 1 term. Right? And I'm just anticipating that p tilde will not be order 1. Right? P tilde will be at least order epsilon. Because when epsilon is 0, p tilde doesn't exist. So if this is order epsilon, then this term is order 1. So I'll have to keep it. Right? This is an order 1 term. Right? Now this term will be small. Right? Because it become order epsilon. This term will be small. So I will not have to worry about these terms. We'll see in a second. Right? When I retain only the leading order, I can get corrections from these at order epsilon square, epsilon cube. But at the leading order, I will not have to solve this whole equation. I'll get an equation which involves only these two terms in leading order. Then I can, of course, correct for it. So now our task is to find an equation for p tilde, solve it to order epsilon, right, at least at leading order, and then I can substitute back. Right? And when I do so, these two will drop out, right, and the leading order behavior will be only here. Already the term we know is L3 phi. Right? What is L3? Just the drift minus d by dx a phi. So that would be the term you would get if you try to write down the Fokker-Planck for x directly. Right? The term you don't know what to do with is that term involving alpha in the original ODE for x. Right? And that's what hopefully will give some kind of diffusion. Somehow diffusion has to come out of this guy. Right? This is drift. These two will vanish. This is your usual drift. Somehow this term has to give me diffusion in x. So L2 has only one derivative in x, right? But that's like the Taylor's problem. Okay, because it has a alpha which gives it the drift velocity a dependence of the fast direction. Okay, so let's keep that equation in mind. We'll return to that. And now we have to go find an equation for p tilde. I'll keep this here. So now we project a full equation onto the range of L1, right? We already did the range complement part. So to get the range of L1, what we should do is take the full equation, subtract out the range complement part. Right? That's all. But now I'm going to make my life simple by saying I'm only looking for p tilde at order epsilon. So let me write out everything and then we'll drop things, okay? So we have the full stuff. Right, so now I'm coming to the right. So I'll subtract out the stuff later. Let's just write the full equation with the decomposition. Okay, with the P decomposition. So in the original equation, I have d dt of P, right? So that splits up in this way. Then I have 1 by epsilon square L1 acting on P. Of course, L1 acting on PS goes to 0. So I get only L1 acting on the perturbed part. Okay. Plus 1 by epsilon, I will have L2 acting on P. Right? If you want, I can write it like this. And now I should subtract out my range part of it, right? So I'll have minus, correct? So this is equal to this. And from here I'll have minus okay, so that would be the full range complement equation where I subtracted out the projection onto the range. Strictly speaking, I mean, what I should do is take the reduced equation we got, which is a scalar in terms of alpha, right? Multiply it by the null space vector of L1 star, which will be some function of alpha. But that is, of course, just 1, right? So it's like all of these terms which are subtracted are actually multiplied by 1. It's 1, so it doesn't appear. Okay, so these terms will ensure that I can actually solve this problem in the limit epsilon going to 0. Why? Because of course this is an equation for P tilde whose dominant term is L1 P tilde. So that was the whole point of this singular treatment, right? So now if I multiply throughout by epsilon square, correct? The dominant order 1 term is only L1 P tilde. So I'll get L1 P tilde is equal to some right hand side stuff, right? Which will all be order epsilon or smaller. Because there cannot be any leading order part, because when epsilon goes to 0, we know P tilde will be 0. So this will give me an equation of the form L1 P tilde is equal to epsilon times RHS. To solve P tilde, I have to invert L1, which is only invertible if that RHS lies in the range. But now it's guaranteed to lie in the range because I have projected the equation onto the range. So this equation is solvable. Original equation will not be solvable. I'll have to subtract out the range complement. Okay? So if we had just proceeded without this projection, again, if in the center manifold, when we try to solve for P tilde by inverting L1, I will be forced to look at what's called the solvability of Fredholm alternative and remove out the range complement, set the range complement part to 0, which will just give me that reduced equation. So okay, here we are already guaranteeing that. Okay, so now if I'm going to keep terms of order epsilon, I multiply throughout by epsilon square, and what you will get at leading order is simply L1 P tilde, right? All of this will become epsilon square or smaller. Let's remember P tilde itself. So I know that, let me write it this way. Okay, at order 1, P tilde is 0. So then if I want to construct a solution, I will say 0 plus epsilon first order correction plus epsilon square and so on. Okay, but I'm just going to get it the leading order term. So if I want the terms at order epsilon, right, what I should do is keep epsilon terms, but wherever I see P tilde, put it to 0. Otherwise, it will become epsilon square because P tilde is at minimum of order epsilon, right? So when I multiply throughout, I'll get epsilon square here. All these terms will be at least epsilon cube, so they will drop out. These two will be epsilon square. So at order epsilon, I'll get nothing. Okay. So nothing is on the LHS. Instead, I'll have some terms here. This will be L1 P tilde. Okay. This will be an order epsilon term only with this guy, because this guy will again throw out another epsilon. So I'll have epsilon L2 Okay, epsilon L2 phi PS will be there. This P tilde will drop out. Okay, and that then all of this will become epsilon square at least. They'll all drop out. Okay, this guy will be epsilon here, but then that is again P tilde. Fine. So that's all I have. So now formally at least I can write my solution. Sorry, there should be a minus sign here because it's all here, right? This is equal to minus that. And so I can write P tilde as L1 inverse. So L1 is an operator. Presume that I can find its inverse. Why? Because this lies in the range. So I can invert it, right? So I don't know what the L1 inverse is yet. I have to find it. But if I know it, I can write formally the solution as P tilde is equal to the inverse operator, L1 inverse, acting on L2 phi PS. Okay, so I have solved at leading order. Okay, of course, epsilon. So I have solved at leading order my perturbation part of the PDF, right? The deviations from the center manifold. Minus epsilon. Thanks. Okay, so the L1 inverse is some operator acting in alpha space, right? L2 is an operator involving derivative of x but also alpha, so I cannot take that, cannot interchange these two because this has alpha, right? And PS also has alpha. And phi I cannot remove out because x is acting on it. So this is the simplest form I can write it. Okay, but now we'll proceed further to see how we can get an expression for this. Okay, so formally now I have solved for P tilde. Okay, so that's the action of, I've calculated the correction to the center manifold. And I can now substitute it in my equation for phi. Okay, again retaining only terms to order epsilon. Okay, so now keep in mind that P tilde is epsilon something. So then what I said here will become obvious, right? When I replace P tilde, I get epsilon out. This will become an order 1 term. This is anyway order 1. These terms will be epsilon odd. Right? There will be epsilon, there will be epsilon. So I want only the leading expression, so I'll retain in this equation terms to order 1. I'm going to drop out the epsilon terms. And so now, right, the leading expression for phi. Remember, phi cannot be calculated unless I do this, right? If I directly put epsilon to 0, I'll just get L1p is equal to 0, which will say p is equal to phi times ps, where phi is unknown. Right? Any arbitrary phi will satisfy L1 p equal to 0. So to calculate phi, I need to do this, right? But the equation for phi now is still leading order. Okay, so I have dou phi dou t is equal to L3 phi, right? And now I'll have a minus coming out. Right, I'll have to replace okay, so this is now my final equation for phi. Sorry, epsilon is not here. Okay, looks good. So now I know what L2 is. Okay, it's d by dx b alpha. I don't know what L1 inverse is. That is the catch. Okay. And of course, if I specify a capital A and capital B that is creating this alpha variable, right, then I can calculate L1 inverse for any specific case. But what I would like to do is find a general result for any such capital A, capital B, right, which is in the Fokker-Planck equation for alpha. So to do that, I will use a general property that I know about L1 again, that it is the operator of the Fokker-Planck equation in alpha. And remember, we had that result that you can write PS in terms of this exponential operator, right? So we'll use that in a second. But first, let's expand this out, right? What this integral looks like. So let me say this term is going to be called, this entire thing will be called T1 with the minus sign. Okay, so what is this T1 now? It's minus integral d alpha, right? That is what is here. And then I have a minus dou by dou x, right, of b of x alpha, right, then acting on L1 inverse. That's right. L1 inverse, which again acts on minus d by dx. So L1 inverse is some operator involving only alpha. D by dx again, b alpha okay. So now I can take that d by dx out of this L1 inverse, right? I can take b out of it also because L1 inverse is some operator only on alpha, right? B is a function of only x. So these two guys and phi, so the function of x, can be pulled out completely from this L1 inverse, right? And the integral with respect to alpha can be pulled inside. Okay, so finally I'll be able to write it. So there are two minuses here, so this minus will survive. Okay, so I can write it in this form. Now I'm going to call this now term 2. So we have to now figure out what this T2 is. Sorry? Huh? Yes? PS is there, yeah. ds, right? D alpha, no? Ah, here, sorry. Yeah. Thank you. Okay, this is fine. So basically you can pull the alpha integration inside up to the point you reach, so this point, right? And then you can pull d by dx outside completely until you reach here. Okay, so that's what's happened here. And now I've kept the x part separate and the alpha part separate. Okay, and I need to now solve for what this integral is, which involves the L1 inverse. So let's do that now. let's keep that equation there. Okay, so was minus integral with respect to d alpha, right? Alpha L1 inverse alpha PS, right? Okay. So now we need to figure out what is this L1 inverse, right? And what is specifically what is the action of L1 inverse on alpha times PS, okay? So here we'll use a trick, okay? We'll consider the integral of exponential L1t from 0 to infinity. Okay, so the motivation is I know that L1 is coming from the Fokker-Planck operator, dp prime by dt is equal to L1 p prime. So L1 inverse is some kind of integral, right, over time. And to get a handle on that, if we consider the following, right, which is some operator, dt. So let's do this integration. Remember, when you have such operator exponentials, you can treat it like a normal exponential, right? So when you do this integration, what will you get? Exponential L1t divided by L1, which is like L1 inverse, right? And then you have to apply the integration limits. So that's what we want, right? We want an expression for L1 inverse. We'll get it in terms of some integral. So L1 inverse times okay. So what we are showing you is that this integral of exponent L1t dt is L1 inverse times some other operator, right? So you have minus 1 here, but here you have this operator, the t going to infinity limit of exponent of L1t. But we already saw what this is, right? This is just the operator that takes any function and sends it to the stationary distribution times the average, right, over alpha. So if we now look at so remember I want to act L1 inverse on alpha PS. So if I think about, suppose I replace L1 inverse by this guy, okay, I'll have, that would be equivalent to writing minus L1 inverse, except I also have this term. So let's consider what this does when it acts on alpha PS, right? So if we note that, right, so this operator acting on alpha PS, using what we had shown before, right, is just PS times the average over alpha, not average, the integral over alpha of alpha PS. But once again, that is just PS times the stationary mean of alpha, which I know is 0. Okay. So that is 0. Right, so this means that I can write, instead of minus L1 inverse, I can use this integral. Because when it acts on alpha PS, this will not contribute anything. Okay? So therefore now my T2 is just integral of d alpha times alpha, then L inverse alpha PS is integral 0 to infinity Okay. And now once again, see, we use the same operator, right? So this right is a solution no, let me say this properly. Yeah, this is okay. Okay, so why do I say that? Because if you consider this equation, dou p prime by dou t is equal to L1 p prime, and I consider the, right, so, okay, I'll write it this way and then it will be clearer. Okay, so what I'm saying is that, again, we remember that L1 is basically coming from this Fokker-Planck equation, right? And if I consider the Dirac delta solution to this, so where p prime of 0 is a Dirac delta, right? That is nothing but the conditional distribution, right? P of alpha comma t, given that it is alpha prime at time t0. So now suppose instead of the Dirac delta, I use some other initial condition. What I should do is integrate the Green's function Dirac delta solution with respect to that initial function, right? But now over the L prime space. So this whole thing will be the solution to this problem. The solution to this problem is just this, because p prime is just, the solution of this is formally exponential of L1t, right, multiplied by the initial condition. So this is the solution to this with this initial condition. But I can also construct the solution to this using the Green's function of this equation, right? And that would be like this, where the Green's function or the solution to the Dirac delta problem is the conditional distribution. Okay? So now I have replaced this way, and therefore this final integral T2, okay, has this very nice form. Right, now I have two integrals. Prime. Instead of this, I have the following, right? So one alpha was sitting here, right? That alpha is there. And this alpha prime came here, right? And I'm integrating with respect to the stationary distribution. Okay, so now what will I get finally is T2 is an integral 0 to infinity dt times now this stuff, right? Which is an integral over alpha prime. So you see what integral is it? I'm saying I'm taking the conditional distribution of starting at alpha prime and going to alpha at time t later, right? So that property is multiplied by alpha prime and then averaged over the stationary state. So this is nothing but the autocorrelation. Okay. So this is exactly alpha of t right over the stationary state. And this, by our definition in the beginning, is d. Correct? So we said we are looking at some stationary process alpha with autocorrelation integration from 0 to infinity of the autocorrelation function is capital D. So this is what we ultimately wanted to do, right? Without having to specify precisely how we are generating alpha, ultimately get an equation in terms of only its properties, right? So the two properties we had specified, that alpha is 0 mean, and that we use repeatedly, right? Including here to calculate L1 inverse. And now we've been able to write the last term in the equation in terms of its autocorrelation. And once again, from a non-equilibrium statistical mechanics perspective, it should not be surprising because the autocorrelation of this kind of stochastic fluctuations is what gives rise to diffusion. Right? You have this Green-Kubo formula and also it's related to that. Right? So here you see that if I am applying a noise in a Langevin sense, correlated noise, right, to drive the system, right, what's important is its autocorrelation. That will set the strength of the effective Brownian motion it is providing in the delta correlated limit. So fine, I have now T2 is just D, which is a huge simplification. And therefore, I can now go back to my original equation, right, and replace it. Yes, so remember all of this simplified, and I can write down T1. So where was T1 now? Right. So T1, I remember I'm calculating the minus of this is equal to D, right? So T1 is d by dx of B, d by dx of B phi D. Okay. And that's the term that was there in the equation for phi. So now let's go back to the phi equation. So now we get the equation for the distribution only in x and t after averaging out the alpha. After averaging over alpha, right, in the stationary regime, right? Or let me write it like this. Right, so it's the average of the distribution in alpha in the stationary direction. Right? So I'll get dou phi dou t is equal to, remember we have L3 phi, but that is just minus d by dx of A phi, correct? And then this other term, which was just T1, right? Plus I have okay, but now you start seeing that it has form of a diffusion-like term, okay, with a space-dependent diffusivity. But this D is sitting out in a funny way, right? So I cannot identify this as the diffusion coefficient because B is sitting there. But what I can do is split this, correct? So I can write this as, okay, so later what we will do is important. So let me keep this equation here and point out that, wait, let's leave this here for the moment. I'll write it again. Yeah. And now I can take D to be equal to, right? Okay, so I can split it and put in the half. So then I will get one by 2 dou x of root 2D times B. Okay. Now, this is like a diffusion term. It's 1 by 2 d by dx, but the diffusion space-dependent diffusivity is sitting inside, right? And it's in this split form. It's not one coefficient. So this is the Stratonovich form of the Fokker-Planck equation, right, which we had seen earlier when we did Ito to Stratonovich. If you forget to see that, you can expand out this term and rewrite this term as half. You can take this whole thing out, half 2d b square d by dx, d square by dx square times phi. Right? You can pull the whole thing inside. That will be the Ito form. And then you'll get a remainder that will give you the Stratonovich drift. Right? So this is exactly the Stratonovich form of the Fokker-Planck. Right? So this whole thing is it's the Stratonovich diffusion in the Fokker-Planck equation. And so therefore this is equivalent to writing the following SDE, right? So dx is equal to, this is the drift term, right? So I'll have minus a dt, okay, which is what we had, plus a dt, okay, which is what we started with, right? But now I have, see, this term, root 2d comes in front of it, right? B sits there as it was, the Wiener process increment with the Stratonovich interpretation. Okay, so that when I look at this SDE and I write the Fokker-Planck, I'll have to take root 2d b the whole square in the Ito version, but then I'll also have the drift, right? But if I directly write it in this way, it's just this term repeated 2 times, but nested appropriately. So the diffusion coefficient is actually 2d b square. Okay. But when you write it as an SDE, you have to take the square root of that, right? Square root of the diffusion coefficient. Okay, so this is a proof, right? So we have, using center manifold reduction, we have shown that if you start with this system, okay, of an ODE forced with a colored noise alpha, where alpha is a stochastic Markov process, right? I can use center manifold reduction in the limit of large timescale separation, average out the alpha direction, and get a reduced equation only in X, which takes the form of an SDE that has a Stratonovich interpretation of the noise term. Right? So in the limit of epsilon goes to 0, that alpha behaves like white noise and appears, but in the Stratonovich sense. Okay? But this is a weak result because I came from the ODE SDE system to the SDE system via the Fokker-Planck. So only the statistics will hold. Right? It's not a strong proof. Okay, so we'll pause here, and in the next class, we will consider what happens when we are in multiple noise dimensions, because that's why I did this, right? The key step at the end. So up to here, everything was fine. It was important that I could take this d and write it as a square root squared. Okay? This is immediate in one dimension because d is a scalar. But when you do multi-dimensional noise, so you have turbulence which has many length scales, many scales, right? Then if d was multi-dimensional, d would be a tensor, and then I cannot always split it. Okay, so that's where there will be a subtlety. So we'll come to that in the next class. Thank you.